Why is power rating so critical? Why is it so important in electronics? We haven't really had the opportunity to discuss it before, so this is a short video. I will just demystify some of the topics around power rating in electronics. In a nutshell, power rating is essentially the maximum amount of power an electronic device, or in this example, a resistor, can tolerate without degrading or damaging itself in the circuit in which it belongs to. So if you see the example to the right, in this example, we have a resistor, and the resistor is likely the power that is dissipated by the resistor is certainly beyond the power rating of the resistor. Sometimes you might go beyond the power rating of a resistor, but it doesn't necessarily burn or smokes. And that's because you're slightly above the power rating. In that case, most likely the resistor will be damaged. Sometimes it is not entirely damaged, but in general, it is no longer a reliable resistor. In this case, you are way beyond the power rating of this resistor, and therefore, as you see here, it is entirely burned, or as we saw on the previous slide, the resistor completely burns. So this is very critical to determine the power rating of a device. And that's what we want to explain to you in this short video. So if you see here, we have different examples of resistors. These are all resistors. This is a resistor, another one, a third, a fourth, a fifth, and a sixth. They all have their own kind of shapes and colors and the different color bands that they have, and which basically means that they all have different resistive values. And one thing that one can notice right away is that they're not the same, right? They're all unique in their own certain way. And if you recall from lecture 2, we saw that the dimension of a resistor is critical. The dimension of a resistor tells us the resistance of a resistor. So essentially, if you recall, this is a model of how to determine the resistance of a resistor. It is equal to rho, which is the resistivity, which has a unit of ohms times meter, times the length of the resistor divided by the cross section, the conductor here, the area of the cross section. And therefore, as you can notice by this model of how to find the resistivity or the resistance of a device, the shape of the resistor certainly impacts the resistance value. So we know that the shape will have some impact, but maybe one thing that we are sometimes led to believe is that larger resistors will necessarily have larger sizes of resistors, like this one. This is a larger size of a resistor, will necessarily have a larger resistance value, larger ohm. Smaller size of resistors will have smaller ohms, and that's not always the case, right? So one has to be extremely careful. Certainly the shape will have an impact. You could see it from here, and you could perhaps go back to lecture 2 to notice this. But the shape and the size of a resistor is really related to the power rating of a device. So here, simply by looking at these different resistors, and they're all placed according to scale, so none of the pictures was shrink or anything like that. And simply by looking at it, this resistor seems bigger than the rest. So right away, without even looking at the numbers below them, you would right away believe that this will have a bigger power rating. This is a smaller resistor. It is physically smaller in size, and therefore it will have a smaller power rating. And this is true. The size of a resistor is always proportional to the power rating of the resistor. Bigger resistors will have larger power that they can sustain. Smaller resistors will sustain smaller power. So this is a physically smaller. It will allow you a small power rating, 1 over 8 watts. 1 over 8 is 0.125 watts. This is a physically larger resistor, and it will allow you up to 5 watts of resistance. But the values of these resistors are not necessarily the same. I mean, this could be in the ohms, and then this could be in the kilos of ohms. So values of a resistance is not necessarily related to the shape of it, to the size of it. And again, we could always see this through here. But what is related to the size is really the power rating of it, and that's why I'm trying to stress on this a lot. So at the end of the day, this is what you need to pay attention to, is that a specific resistor cannot be used for every application. Right? You have to be careful. What is the application that you're trying to do? What is the electronic device that you're trying to do? What is it trying to, what are you trying to attempt with it? Are you building an electronic device for an AC, or is this an electronic device for a heater, or is this an electronic device for a calculator? They will all have different power rating, different utility, different utilization, different use cases. So this, you have to be careful when you use a certain component as opposed to another. Oh, it is always important to determine the amount of power that a specific resistor can sustain. So it's no longer just figuring out the resistance, the R of a resistor that you want, but you also need to determine, does it meet the power rating of the circuit that I'm building? Because this could be very damaging. If you put a resistor, it has the proper resistance that you want, but it doesn't meet the power rating of your application, it will burn. And if it burns, that creates it will damage this component itself. It will literally burn. It will smoke. But imagine if it is connected on a motherboard or on some board, some electronic board. It will damage the entire system, and it could be very, very costly and also very dangerous to have. So this is very critical to understand the power rating. I think we will understand a bit better, perhaps through the example that I'll show you on the next slide. So let's consider this basic circuit. We have a DC source of 12 volts, we have a load of 800 ohms, and we need to find the power dissipated by this. So what we could certainly do is we could either find it directly through through a combination of Ohm's law and Watt's law. And in reality, we could just find the power directly. We could just use P is equal to V squared divided by R. But let's say we don't know that. We simply know P is equal to VI, and we want to go through Ohm's law. So we determine the current. It's 15 milliamps, or if you use your probes on with your Multisim Live, you'll find it's 15 milliamps. And then you simply multiply through. And that gives you roughly exactly 180 milliwatt, or roughly 0.2 watts. Okay, so we know that this resistor will dissipate 0.2 watt. And now the question is, we want to build this circuit in real life. So we go and maybe we check the different resistors that we have in our toolkit, and this is what we have. We have these bunch of resistors. And now the question is, which one do we pick? Which one do we pick? We have no idea what the values are. We simply know that they're different. Different resistors, different shapes, different color bands. We could kind of go through all that. But as a first step, you have an inkling, or you have some insight about the power rating of these devices. Okay, so you know the power rating of this one is 0.125 watt. This one here is 1 divided by 4, which is 0.25 watts. This is 0.5 watt. 5 watts, 2 watts, and 1 watt. And in fact, you notice that, or you could right away kind of organize that because of the shape of it. Larger resistor, larger power rating. Smaller resistor, smaller power rating. So according to what you want, you could directly eliminate those that don't make sense. So if you see here, this right away doesn't make sense, right? You can never use this. It has a power rating of 1/8 watt. So this is 0.125 watt. And you know that your circuit will dissipate 180 milliwatt, or if you will, roughly 0.2 watt. So this one here will never be possible to function for this circuit. Without even looking for the value for the resistance, you know this one will be wouldn't be practical. It will burn if you use it. It goes beyond its power rating. So this is right away one that you could eliminate off the bat. So now you're left with the following 5, and you don't know which one to pick. So as a next step, what you could then do is perhaps look at the power rating of all the rest. Does it work? This has a power rating of 0.25. This is 0.2. So 0.2 is within 0.25. This would work. This has a power rating of 0.5, which is larger than 0.2. This would also work. This has a power rating of 5 watts. This would also work. This has a power rating of 2 watts. 0.2 is a subset of it. It would work. Same thing here. So it would work for all of them. So the power rating is checked for all the remaining 5. So now as a second step, what you need to do is you want to find which of the following resistors meets what you want. You want something around 800 ohms, somewhere around that. So the one that will get you a value around 800 ohms is the one that you select. So we'll go through the rounds here. And we could check it either with a DMM or, if you will, with the color bands that we saw in lecture 2, we could determine the resistance. So this has a resistance of 560 ohms. It's not what we want, so this is a no-go. If we look at the next one, this has a resistance of 68 mega ohms, a huge resistor. You want 800 ohms, so it's not what we want, so it's a no-go. If we look at this one here, it's a big resistor, but it only has a very small resistance value. So notice the size don't mean much for resistance values. They have an impact, as we saw in the model, but they don't necessarily correlate to a higher resistance. At any rate, we look at this, and that's 22 ohms. We wanted 800, so this is also no-go. We look at the next one. This has a value of 110 ohms, plus or minus 5%. This is also a no-go. Now we're really hoping that this last one would work, because otherwise we have no other components in our toolkit. So we check this. It has a resistance through the color code, so we could just check it, of 820 ohms, plus or minus 5%. In fact, you could also use your DMM to determine the resistance of the specific resistor that you're holding in your hand. But let's say we don't have a DMM. We simply check it by the color codes. We could just maybe figure out what this 5% tolerance is. Again, if you need a refresher, go see lecture 2. This gives us a value somewhere between 779 to 861 ohms. So now this would work with this, because your 800 ohms will be somewhere in this range. So this would work. Also, the power rating would work, because it has a power rating of 0.25, and you need to be less. Your watts that is dissipated is 0.2, so certainly you're less than this. So absolutely, this one here would work in a perfect match. This one here. So right away, you notice how we narrow it down to find the resistor that we wanted. Okay. Of course, with experience, you'll be able to find the proper resistance much quicker than this. So a combination of both skills to know what is the power rating that you have, so that you don't go beyond it and burn your device, and to find the proper resistance values. So if you will, I mean, just to put it in a kind of an algorithmic way, I mean, there's really two conditions here. First condition, find the resistance that meets the desired power rating. And then number 2, identify the resistors with a proper resistance value. You need both of these conditions when you select a resistor. Okay, thank you for your attention.